Hi there, Mr. Sutton bringing you this lesson on motion. In this one, we're going to be using derivatives to determine the velocity and acceleration of moving objects.
For your warm-up, here's some blanks to fill in. Let's see how much you know about distance, displacement, acceleration, velocity, all that stuff. So pause the video, give it a shot. All right, so first important concept, displacement or position. This is our distance from a starting point, which we'll call this s of t if we had to give the function a name. Velocity, that is going to be the change in position over time. So we can call this v of t, or this is actually the derivative of position, s prime of t. Speed, this is going to be the absolute value of velocity. So this can never be negative. Units of velocity, for example, we could use meters per second, pretty much anything per second. Acceleration now, that's going to be the change in velocity over time. We can say a of t, we can say v prime of t, because this is the derivative of velocity, or we could say s double prime of t, this is the double derivative of position. So these units are going to be meters per second squared, or feet per second squared, something like that. We could go even further. We have third, fourth, fifth, and sixth derivatives of position. So the third derivative is jerk. Fourth derivative is going to be snap, unofficially anyway. I think officially it's called jounce. And then crackle is the fifth, and pop is the sixth unofficial. But really, we mostly deal with displacement, velocity, and acceleration. For the next several examples, we're going to use this problem. A dynamite blast propels a heavy rock straight up with a launch velocity of 80 feet per second. It reaches a height of s of t equals 80t minus 16t squared feet after t seconds. And let's figure out all this stuff about this situation. So this first one, how high is the rock after 3 seconds? We're just asking for the position when we plug 3 in for t. So we can just use the original formula for this. So this is going to be 80 times 3, 240, minus, let's see, this is 9 times 16, so that's 144. So that's going to be 96 feet for that one. Units is feet. For our next question, at what time will the rock hit the ground? Pause the video and see if you can figure this one out. All right, so we need to figure out where s of t equals 0. We want the output, the position, to be 0. So we can set this original function equal to 0 and solve. We can take a 16t out of both of these. That'll be 5 minus t equals 0. And then we have 0 and 5 as the t values that will solve this. But now they're asking for time after the launch. So really 0 doesn't count. It's just the 5 seconds that we're interested in here. For this next problem, we want the average velocity of the rock over the first 2 seconds. Pause the video and see if you can puzzle this one out. So since we're asking for an average, we want the AROC formula. And for velocity, that means it's the average rate of change of displacement. So we're still using this distance formula. So that means we're going to have, for the first 2 seconds, we need s of 2 minus s of 0 all over 2 minus 0. S of 2, that's going to be 160 minus 64 if we plug 2 in there. And s of 0 is just 0. So all this over 2, 96 divided by 2, that's going to give us 48. And our units is going to be feet per second. On this next one, they want the velocity and the speed of the rock when it hits the ground. So now we're talking about, this is talking about instantaneous velocity, instantaneous rate of change. So we need the derivative of position now. So v, or s prime of t, that's going to be 80 minus 32t. And then we need to figure out what the time is when this hits the ground. Now, the good news is we actually already figured that out on one of the last examples. We saw that time was 0 and 5 when the position was 0. So 5 seconds is the time we're going to use for hitting the ground. So let's plug 5 in for t here. So that's 80 minus, this will be 160. So that's going to be a velocity of negative 160 feet per second. Now, they also want the speed of the rock when it hits the ground. Velocity can be negative, speed can't. Speed is the absolute value of velocity. It's how fast you're going regardless of direction. So we need the absolute value of our velocity, which means we have a speed of positive 80 feet per second. This problem's a little trickier. At what time between launching and landing is the rock at rest? Now this notation, this wording is a little bit tricky because if you think about what's happening, you're throwing this rock in the air, it's coming back down, and you're thinking, well, this thing is always moving. It's at rest maybe when it's on the ground, but we know that happens, at time 0 and after time 5. But they're asking between launching and landing. So the key to this is realizing that the rock is at rest technically when it has no velocity. And that does actually happen. When you launch this rock up, it's got a positive velocity. At some point, that velocity becomes 0 before it can become a negative velocity on the way back down. So we need to figure out where our velocity equals 0. The good news is that we have a velocity formula, and we can set that equal to 0. So that was 80 minus 32t. We can set our velocity formula equal to 0, and now we just solve for t. Subtracting 80 and dividing by 32, that's going to be a t-value of 2.5 seconds. For this next question, we're asking what time does the rock reverse directions? See if you can come up with a strategy for figuring this out. So to do this, we're going to have to use sign analysis on our velocity function around those critical values. The velocity is telling us what direction we're going. So to reverse directions, we have to change from negative to positive or positive to negative. So that means we need to know where the velocity is 0 and test around that. Well, we already know that our velocity function, 80 minus 32t, equals 0 at 2.5. So we can make a little sign analysis chart here. Here's 2.5 seconds. Let's just test values before and after that. So at 0, our velocity is going to be positive, just 80 minus 0. And then if we plug in 4, 80 minus 4 times 32 is going to be a negative. So since the sign changes at 2.5 seconds, we know our rock is reversing directions at that time. For this next question, we're asking the maximum height of the rock. This is like any max problem. We need the derivative of the original function, sign analysis, and we need to be changing from positive to negative. Fortunately, we've already figured out where s prime changes from positive to negative. We found out where it was at rest. We did sign analysis on the last example, and we saw that at 2.5 seconds, this happens. So we just have to plug 2.5 into the original function, and that'll tell us what the maximum height is. So take a sec to do that on your calculator, and hopefully you ended up with the same value I did of 100 feet. Try this next one out based on what we talked about in the very beginning about what acceleration actually is. So acceleration, remember, is the derivative of velocity. We already had a velocity function of 80 minus 32t. So the derivative of the velocity, the acceleration then, is just going to be negative 32. Now this is a constant function of negative 32. So if you plug in 3 seconds, you're still going to get negative 32. And be careful about our units. We're going to have distance per time squared as our units. This next problem is one of the more common problems on the AP test about speed. Here they're asking if the rock is speeding up or slowing down at 3 seconds. The key on this one is knowing the relationship between acceleration and velocity. If you have a positive velocity, then a positive acceleration is going to keep adding positivity to that and make you go faster in that direction. If you have a positive velocity, a negative acceleration, of course, will slow you down. But it works the other way around as well. If you have a negative acceleration, negative velocity will speed you up, and a positive acceleration would work against it and slow you down. So in general, you have to look at the signs of velocity and acceleration. If they have the same sign, they're working together in speeding you up in whatever direction you're going. And we don't care about the direction with speed, it's just absolute value, right? If the sign of velocity and acceleration are different, they're working against each other and they're slowing you down. So velocity sign, take a sec to compare that with the acceleration sign at 3 seconds. So velocity at 3, that's going to be 80 minus 96. That's a negative number. That's really all we care about is the negativity or positivity. The acceleration is always negative 32. So at 3 and every other x value, t value, that's going to be negative. Since these have the same sign, that means they're working together and we're speeding up. So at this point in the presentation, our velocity is at 0. We have come to rest. This is it. This is the end of it all. Until next time, Mr. Sutton signing off.